Hello and welcome back to Algorithm Coding in Leaf. Today we're going to talk about big O notation. If you don't know who I am, I'm edA-qa mort-ora-y, and I do a lot of different streams, and this one's about my language Leaf, but in particular how we use it to do algorithms and analyze complexity. You don't really need to know the language. I'll walk you through that. Last time we talked about time complexity, and this week we're going to show the step you take to get it to what's commonly known as big O notation. We'll talk a little bit about what that is, how we use it, and how it can help you, and some of the misconceptions of it. If you have any questions, just feel free to ask, pop in the chat, or just say hi. Otherwise, I'm going to get going on this and start with where we were last time, and that was in time complexity. And we were using this code from Leaf, and we had the basic example of some numbers. And we talked about when we had time complexity, where we were counting the number of times a certain operation took place. In this case, we wanted to say total, how many times we had a total, and that was n operations, so we did it n times. We may also want to count this and this, but that's how we end up saying that it was Tn of n. And I'll write that one down again. So we had T of n equals n. And this was pretty straightforward. And this one, you may not see this, you may not understand so much how we go to complexity here, so let's be a little more strict here. Instead of saying n, why don't we say, we're going to count this one, every operation on total, so we have something like n plus 2. Even more, what we want to say is that let's expand the code a bit first. And the reason I'm doing this is to show how we actually get from here to big O notation. So now we access total. Let's say every access to total, whether we're adding or subtracting or doing anything, assigning, costs us 1. And that's how we're going to modify the time here and say, well, here we access once, so once here, and twice here, and once here. So we actually have 2 times n, with the wonderful font here. I'll try to write that again in a second. So we have 2n plus 2. Alright, 2n plus 2. So that's a little bit clearer. Let me erase this other bit here. And I'll show you how we get to the big O notation of this now. And you guys are probably quite used to this, seeing quite often that when you say this algorithm, instead we often say it's O of n. And we're wondering why. Why is this the same? Why is this equal the same thing? And the time of n is actually 2n plus 1, and the O of n is just O of n. It's just n now, yeah? And the reason why we do this is, why do we say, why does this value go away? And why does this one go away? And this has a lot to do about what O of n actually means. What O of n is compared to this actual time number here. And this is where it gets a little bit confusing. Is this a time of n? This is an actual function. This is a complexity thing. And we'll often see just an equal sign, which is technically incorrect but used everywhere. So it's not actually incorrect anymore. And so when we say O of n, what we're talking about is the upper limit here. So there's going to be some place. So if we drew a little graph for this, we might want to actually say this function, some numbers, as it goes. So you might have a time like this. This is fairly linear, and this is okay. We have the first 2 there, but we have for big O notation, what we're saying is we have a line that at some point goes like this. So we'll say it's linear, and enjoy my drawing. If you don't like my drawings, it's super. I'm doing this with the mouse. If you want to help me get a tablet to make this better, go off and join my Patreon campaign, or subscribe to this channel, and I'll put all the money back into buying equipment to making this all better for you. But in any case, this is what we have here is, if you take the normal thing, if we say n, if we say this function is just n, you'll notice a little bit at the start here, and this is in particular up to the value of 2. Ow, that made it messy. Sorry. Somewhere around here, our actual t of n function, 2n plus 2, is bigger than n. But at some point, this line, somewhere around here, and let me guess based on the numbers, this is going to be 2n, yeah, somewhere around 5. The line can actually get bigger, and when we say O of n complexity, what we're saying is that there just has to be some number, so x times n, which is greater than t of n. And I'm going to lose that right away, aren't I? Alright, so let me try it again. So what we're saying is that there's some number called x. This is terrible, this thing. Really need that drawing from x times n is greater than t of n. This is the basics of time complexities. What we're saying is that this is the upper bound on it. As long as at some point in this graph, if you shift this line, you multiply it by some value, as long as it can be bigger than all of these values n, it's actually greater than or equal to. And this is the basis of big O. And it lets us ignore the small details, because what you have is we're saying at some point this small number just doesn't matter. This line is high enough that that plus 2 is going to be insignificant. And this 2 here goes away because we actually say it's something times it. And it doesn't matter what x is, we're just saying multiply it by x. And so this is what it means for big N. Is the rules basically come down to in common use. You don't have to clearly understand this. The rules for common use are basically drop all the constants and drop the multipliers and just take what's left. So 2n plus 2 becomes O of n. And we say this is a big O of n. And what we mean by this is that this algorithm will never take longer than n. Well, it'll never take longer than this. It could take shorter than this. But our algorithms tend not to. Most of the time we say that they just don't take longer than this. And that's usually an upper bound. So if you're specifying the bounds of an algorithm, you want somebody to write something for you, say, hey, look, it can't go slower than this. And again, remembering measuring the worst case. So if we went down, we had another example in the code. Let me clear all of this. In this index of function, remember we agreed last time that even though it depends on what you're looking for, that the t of n of this, how many steps it takes, the time complexity of n, is still n. We didn't care the fact that the number may be the first one in the range, in which case it took 0 steps. We didn't care it might be in the middle. We said we're talking about the worst case, and in the worst case this takes m steps. But then you might say, well, okay, what if I care about the average case? So we no longer care about the worst case, we want to care about the average case, in which case this is equal to n over 2. Now what's interesting here is that when we put this in time complexity, in big O notation, both of these are just O of n. Because this n over 2, if I erase the n here, is actually 1/2 n, and we said we ignore those values. So we get rid of these, we just ignore them and just say it's n. So even if we consider the average case here, we wouldn't care. The big O complexity is the same of this algorithm, because they're both bound by this O(n). They're both bound by this amount. The only way we can get this number down is by reducing the power exponent of these. So these are both power 1. And the typical one you see for this is a binary search, which is log n. And a binary search is log n. And I can open one of those up so you can see what a binary search looks like. We did one of those on the show a few weeks ago. And just ignore the stuff on top for a second. Binary search. And you'll notice we created these two functions, binary search, and it's a rather complicated code. You can go back and look at the show and see how it does it. And this is a case of why we use big O quite often, is because the actual time complexity, the t of n of these two functions, is not so trivial to calculate. There's a lot of steps involved, and we're not quite sure what we actually want to do with this. Which ones are we counting? Are we counting the comparisons? Are we counting the individual searches? Are we counting the return values, the increments? And so what we say is we say, well, I don't actually know what the t of n of this is. Let's erase everything. So again, so we're going to say, what is the t of n of this? I'm going to say, I don't know. I don't know what that is. But I can look at the algorithm and say, well, there's some recursion involved here, and I know how it works. And I know it splits off to half each time. I know there's a log n number of recursion steps. And it doesn't do more than that. So whatever it does, for sure, it's O of log n. Because it doesn't do more than that. It just doesn't do more than log n steps. And this is one of the conveniences of saying big O notation, is that I don't have to specifically find out. I can very generally, roughly say, look, this is big O of log n. I don't know the specific steps. If I really wanted to, I could, but that's enough for me to know the class of algorithms this is in. And so this is really helpful in this regard. It's one of the reasons why we use big O quite a bit. But you'll notice in this thing I have a bunch of thetas in here, and I also have a big omega. Now let's look at go back to the other code to explain that a little bit first. And again, if you have questions, just ask. Otherwise, I'm just going to keep talking about random things. And if you have questions offline, just feel free to send me off a notice. I don't mind doing these shows again to address specific questions. Complexity is actually a rather difficult topic. And actually, as a sidetrack, why don't we just go over to Wikipedia for a second. I can show you how they describe big O notation. It's a fun little thing because it's not actually that difficult of a concept to intuitively understand, but the mathematics behind it is a little bit weird. And so they have this definition. Oh, it's zooming really slowly. So you'll notice this definition they have right here of big O notation. And again, they even use equals here. If you scroll down in the thing, you'll actually see they say whether belongs to actually makes more sense. And in a way it does, because if you take our algorithm, and I'll go back to the blank page for a second. Oops, get away this thing here. I have a blank page here somewhere. When we say that t of n plus 2 equals O of n. Sorry, this is just lovely drawing. When we say this, this can often be very confusing because we're saying it's equals, but this is not your typical mathematical equals. If you look to the history of big O notation, this is abusing the syntax a bit to say this is one-way equals. And what is often clearer, if you're trying to understand what we're actually saying, is we're saying t to n plus 2 actually belongs to O of n. And this, I think, makes a lot more intuitive sense, because the first line up here, it says it's equals, and if you look at math, quite often equals means it both ways, but certainly not. O of n does not equal t of n plus 2. I can guarantee you that. If the algorithm is A-plan, and it doesn't even make sense to put the t here, it's a little bit weird. And so what we say is that instead, these time complexities belong to it. So these O notations, these are sets. If we had set notations, these would be sets, and we can say stuff belongs to the set. And this makes a lot more sense, because it's no longer equals. Our time complexity is not O of n, it belongs to O of n. And this is how it's a lot easier to understand how you can drop off constant stuff, because it's not an equals relationship. It's a container relationship, it belongs inside of it. So if you have all of these big classes, we call this big scope O of n, we have all these subclasses and functions that belong inside of here. And this is why it's often more convenient to say it belongs to rather than equals. But you'll notice the commonality, and by convention, we always say equals. Even if equals is not the cleanest way to express this, it certainly makes sense. And this next part in Wikipedia right here, This is just their way of saying it's an upper bound. This was the graph I did. This was the graph I did. So if you have a graph and you have some line, this is just some function saying something takes like this over time, and the upper bound is saying we have some straight line, and this is again for linear. We're going to have some line which at some point becomes higher than this, and it's guaranteed after this point to be higher or equals to. And that's all big O complexity is saying, is that these are the upper bounds to the function. Now this doesn't explain why in a lot of my code you'll often see me using big theta instead. And there's also something called big omega. And so let's look at a big graph again for this. Ignoring all numbers, let's just draw a graph of what could possibly happen here to understand what these values could mean intuitively first. So let's draw a silly graph. Let's just draw something. Let's just say it takes a lot of time, it evens out, then goes above, and just something like this. We're saying this is how long this takes. So this is n on the bottom. We'll say this is n. And this is time up here. So time is going that way. So it takes more operations as n increases somehow. This may be linear, may not be. And we're going to see this is a kind of linear relationship. And we're going to look at some point we can take a line and draw it across the top. And this is our O of n. Oh, I got to turn that off. And we can also, that's our O of n. We can also draw a line across the bottom. It doesn't go below this line either. Now these are both linear, so this bottom one is O of n, and this top one, oh sorry, this isn't O of n, this top one is n. Let me erase that. Oh great, I lost my line. There it is. So this top one is n, and this bottom one is n. And so just imagine that way. We've taken whatever formula this is and we said, just reduce it to n. And again, we said this could be multiplied by some value, or we could have some base offset. It doesn't matter. The point is this is a linear line, so we're just calling it n. And the fact that it's an upper bound makes this O of n, big O of n. And now the fact that it's a lower bound, the lower bound then, we just call it theta of n. Let me erase that bit. And those are the difference between the two. We have an algorithm and it's theta of n and big O of n. These form a range. If you want to express this in other notation you would have to see in math, or if you're dealing with normal numbers, you might want to see it like this, that theta is less than or equal to t is less than or equal to O. That's the relationship between big theta, the actual equation, and O. Which one looks like theta? Sorry, this is supposed to be omega. If I said theta, I'm sorry. And this is big O over here, or big omicron, but nobody says that, big O. So we have theta on the bottom, I'm sorry again, omega on the bottom, and O on the top. And these are just the lower and upper bounds. And when we have this relationship where they're both n, this is why I often say in my shows, I'll use theta. This is the actual theta. This is the theta, yeah. This is theta here. This fun with the line in the middle. You want to draw a wider line. Theta n means that the omega and the big O have the same value. So that's what theta of n means. It means it takes the same time. And for computer algorithms, this is very much desired. Yeah, theta and big O often get confused because most of the time when analyzing, most of it, not always, most of the time you actually care about theta and not big O. But as I say in my other shows, because we don't have a big theta on our keyboard, it's much easier to type big O. Technically you don't have omicron, but it's indistinguishable from O, so it works just fine. And so let's clear this off again, and let's look back to what I mean about that in our simple example. If we go back to, where is that? if we go back to the sum of the numbers, we said the time complexity of this in our new formulation is 2 plus 2 times n. And the upper bound of this, since it's a fixed amount, that means the upper bound is going to be just n. And I got to get my character selector now, since I'm typing. You can see why we don't use omega too often, because you actually have to go and copy it from somewhere. I've actually tried to get it set up on my keyboard. I have an open question on one of the Stack Exchanges on Ubuntu about how I can get it, because I have a dead Greek map character, but it never works. Okay, so we have, because t of n is variable, we've reduced it to n in both cases. The omega and the big O are both n, which then also allows us to say the theta is n, and let me go copy the theta as well. Just got to copy them each once. Oh, and this is always lovely. When you close the program for which you copy, it closes, it cleans the clipboard, and that has always annoyed me. And this big theta here, this is actually saying exactly this, that the omega and the O are exactly the same. And we get omega and theta of n because we have 2n plus n, and we followed the rules of just saying we'll drop the 2 and drop the 2 here. We drop that. And so let me give you another example of that. I can just do it in code here of how we get big omega and how we can drop things. We have this checker pattern here, and it does an inner loop, and it's going to be an n times n, and we simplify and just say n squared. So let's go, actually I can do it right here. So we say the time complexity of this is actually t of r times c, and we actually say there's some stuff, so there's some constant x, and we do some other stuff. If you see the outer rows, we do some outer stuff, y times r times rho times, plus we do some stuff inside of here. Again, we don't care what the stuff is, z times c times r times. Now this is actually the time complexity of this. This x, y, and z, these are just constant values. We don't know what they are. We don't care what they are at this moment, but it lets us simplify. And we're also going to say that c is roughly equal to r. There's actually a lot of reason to do this, and in algorithmic complexity it simplifies a lot, because if you have a program like this, say, well, they are going to be equal, they may be 1 or plus or minus, it doesn't matter. Let's just say they're equal to r, and let's just say it's n. And this all simplified then becomes to x plus y times n plus z times n squared. And if we want to go to big O complexity, we can reduce this and say this belongs to a class of problems called n squared. It's not equivalent. We've dropped the x and we've dropped the y, because again, this is based on the rule that we fact. It doesn't have to be n squared itself, which is greater than it. It just means that it's some constant value of it. So if we have t times c times r is less than or equal to, actually it belongs to, and we actually say a constant times that. And again, this is the math on the Wikipedia page. Just imagine this is an upper bound, and you can shift the line up however far you want. But you'll notice again that there's nothing variable about this equation. It never takes less time than this. It's always this amount of time. So that's why we said it can also be, I'm going to copy it down here because I don't have the symbols. We also say it's omega of n squared because it never takes less than this time. It's always n squared, which means its theta is n squared. Now this is what you see a lot in computers then. When we say big O, we might mean big O, but quite often when you're analyzing actual algorithms, you tend to mean big theta. And that's the vast majority of everyday algorithms you see in computing, is they don't have variable time. They take a fixed amount of time. And it's based on the size of the input and not necessarily what you're looking for. And so we could say they're big theta. Now if we look at index of, you might want to be tempted to say, yeah, but index of, we specifically said it doesn't always take n. Sometimes it takes 1, sometimes it takes n, and sometimes it takes half, the average would be half that time. And this is where I made the case that you have to be very careful about what you're measuring. We have a worst case here. T of n equals n. That's how long it's going to take to find an integer in this list. Actually, T of n, say, plus 1, because if it doesn't find it, it has one extra operation to do. We can count return statements. What's the best case we have? T of n equals 1. This happens in the case where the integer happens to be the first one. So we have two time complexities here, and one does not involve n. So what is the big O here? What class of problems is it? Well, even ignoring what we mean, big O has this interesting property that says, okay, this is the upper bound. Well, n is certainly greater than both of these. So is n squared. So is n cubed. So is 2 to the n. 2 to the n. So is n factorial. These are all way bigger than that. And this is one of the problems of big O, because it says it's an upper bound, but it's not a tight upper bound. So if we go back to this first one where we say some numbers, let's ignore that first. Say if you're in a class and somebody says, well, what's the big O of some numbers? You're like, what do you mean, what's the big O? What's the upper bound of it? Well, you're fair to say this is n to the 8th. It doesn't take any longer than that. I have to put these all in comments. But this information is utterly useless to people. An n to the 8th algorithm is ridiculously long, especially for summing the numbers. If I told you that my sum numbers was big O of n to the 8, you'd laugh at me, but I'd be like, well, no, it's actually constant time. They're like, what? No, but you said big O. It's like, that's because it's big O. Now, this is where we say, and this is the second thing here, is that omega is the lower bounds. So what's the lower bounds? What's the lowest possible bound you can have is 1. This is not helpful either. You can say this of any algorithm. The lower bounds of this algorithm is 1. It's always less than how long it takes. This doesn't help anybody. And this is why we have Big-Theta. Because Big-Theta says that these bounds have to be the same. It makes them tight bounds. It says you're not allowed to do that. So if you're in a class and your professor then asks for big O, I wouldn't actually try and say n8. You would assume that he means what's the theta? How long does this algorithm actually take? And so in that case, when we have a theta with these two numbers, we don't have one here. There is none because we said n8 and 1. But if we set it up here with big O of n and theta of n, omega of n, then theta of n is true as well. We actually have theta of n. And again, to get this correctly is what we're actually saying. Let me get a character select again. There's an belongs to. Here's what I want now. The relationship is what we're really saying is this. T of n belongs to theta, omega, and n. And that's what we're saying all of these relate together. This is the upper bound. So this is the upper bound. Upper bound. Oh, I can't type today. Unfortunately, it's not about my keyboard. Although I could buy a quieter keyboard. That's one of the things on my list of things to acquire. And then if we have an upper and lower bound, we basically say it's a tight bounds. They're both the same. We're saying O equals theta. O equals theta. They have the same class. And that's it. That's the way why we have theta, but the big O is the one that's most commonly quoted, and the big O is the easiest one to get. And it's because of this belongs to is why we can drop out values, because these mean specific sets of values. And if we have different ones, a different O and a different omega, you don't have a theta anymore. An algorithm that was truly big O of n to 8th and omega of 1 doesn't have a theta. So let's take that and go down to our print checker pattern again. And actually, no, our index of. Our index of, when we said that our worst case is t of n, best case is t of n. Big O could be anything we want. Big O is n. But here's where the tricky part comes again. When we say big O, you have to pick what you want. This is the big O of the worst case. Right? This is actually common. You have to know what you're speaking of. And we're saying of the worst case. But what if we mean, well, what's the complexity of this of all cases? If we take all the input, and I'm going to add average case here as another input. Average case, t of n equals n divided by 2. Because it'll by average find it halfway through. If we want, of all possible inputs, well, t of n then, to copy my symbol again, and I'm going to copy the right one now so you understand, it does belong to O of n. But it also belongs to, I hate this copying, somebody has to get my dead keys working on the keyboard. It seems to be a defect in either in Kubuntu or the X desktop. Okay, and this is lower bound. So what we're saying is if we say of all possible inputs to index of, it has an upper bound of O of n. That's what O of n means, upper bound. And it also belongs to omega 1. It has a lower bound of 1. And these are both as close as they can go because we know it can be constant or we know it can be linear, and therefore it has no theta. This function, if we want all possible inputs, does not have a theta bound space. Now it says something interesting about it as well. And the reason why this is so important is, let's say you're doing, cryptography, and you had an encrypt function, or you had let's say a decrypt function or find primes. Let's say you have a find primes function of a number, and you want to know how long this takes to run. Well, it's quite possible that in the worst case, I actually don't know what this is. This is, how long does prime factorization take? Is it 2 to the n? I don't remember. 2 to the bits or something like that. This is a long time. A very long time, let's say. So for the bit sizes increases. This is great. You want this. But what if the find prime algorithm what if it has a theta of 1? I mean, an omega of 1. What if there's some cases where it actually comes back immediately? What if the algorithm, like for 10% of the time, t of n equals 1? Or even worse, t of n equals n, and you could say n. That would also be really bad, so bits. If this find primes can actually come back in a linear time based on the number of bits, this encryption algorithm is absolutely worthless. And so this is why in cryptography, you'll often find the other side. They don't care about big O. They care about omega. So they want omega of 2 to the bits. Who cares if it has an upper bound? Even better, if for 10%, maybe for 10% of the algorithm, so maybe the upper bound is really like 2 to the bits or something, right? This is even better, but nobody cares. Everybody cares in cryptography about the lower bounds. So in cryptography, lower bounds. How fast could this possibly take? And this is why big omega is really good in this case, because you're saying, look, it can't take less than this. I don't care what you provide to this algorithm. It's not going to take less than this. And this is one of the cases where you won't use big O, where you use big omega. Now, if you happen to have a theta of the same, if you happen to have a theta of 2 to the bits or 2 to the n, that's fine, but you care about the lower bounds. And this has a lot to do why, when you're dealing with big O, you kind of have to know what it means. But again, let's draw another chart here and just say, so you know roughly, even without knowing specifically what they mean, because again, if we go to the if you go to the actual definitions of these they're not that hard to understand if you understand all the symbols and you really can read all of it. But they're easy to understand if you already know what they mean intuitively. And so let's just do it as a way to finish off. Let's do one more. What do these things mean? And if we're going to draw a graph, a very poor graph, again, I need that tablet. And we're just going to draw some a random equation here. And usually equations get weird at the start and then they even off over time. And maybe this one's actually linear or something, or logarithmic. These tend to be bound by some function on the top and some function on the bottom, and they're contained in here. The function that binds them on the bottom is usually expressed as omega, and the function that expresses it as a top bounds is usually expressed as big O. I'll get a perfect O because I simplified that. And that's what you have to understand. And if these two are equal, then you have a theta in the middle. And this is actually a bad place to put theta, but it says they're equal. And if you think of it in terms of this way, big O is the upper bounds. And just remember, it's not a tight upper bounds. This O can be as high as it wants. And that's why we have theta. We're saying, no, theta means they're tight bounds. And I've actually not found a symbol that means there's a tight upper bounds other than theta. And there's a lot of reasons for that, but we don't have to get into now. Remember, primarily when doing algorithms in computer science, you're interested in the theta. And let's go back to the code again. So this theta over here, and that means you have an upper and lower bounds, which are the same, and they're at tight bounds then. This one here, because they're both linear, would have a tight bounds, so it would also be theta. If you're dealing with some cases in encryption, you only care about this lower bounds, because you want stuff to take at least this long. It's not allowed to take less than this. It can take infinity, that'd be great, but it can't take less than this time. If you're specifying the requirements from an algorithm, so you're saying I need a search algorithm, then you'd actually say you're going to specify the big O. You're going to say it can't be more than O of, it has to belong to O of n squared, which gives a requirement for the programmer. If you're being asked to analyze an algorithm, then chances are you're being asked to find theta, because otherwise big O and analyzing big O and big omega is actually really simple, because big omega can basically always be 1 and big O can basically always be n factorial, or 2 to the n. Actually n factorial is always more n factorial, because they technically belong to that. It's just not useful to anybody. So usually we ask about theta and sometimes about omega. And yeah, big O is usually meant for specifying algorithms, and you'll find this in language standards. And I hope this helps a little bit. I know it's a confusing topic, but I wanted to go over a lot of it sort of briefly. And if you do have specific questions, please get back to me, or if you need to see this again with the better drawing thing, that's fine too. I go through this a lot, and every show I'm going to come back to this. I just thought I'd have a special episode dedicated just to this. But if you're watching another show, like ones where I analyze algorithms, for example, when I analyze the binary search, and I start coming up with this is big O and this is big theta, or this is big omega, or if I start talking about space complexity, just feel free to call me out and say, hey, I've forgotten what that means, can you tell me? And I don't mind going over this again. I just wanted to have one basis so people can find it, and I can talk just about this. I think that's it for my show. Thank you for watching again. Follow me on Twitter and ask any questions you have there. If you want me to improve my on-screen drawing graphics, please subscribe to my Twitch channel or become a patron of mine on Patreon, and all that. Anything I get through those, or cheer for me in Twitch, all of that will go towards purchasing, improving the hardware. Whether you don't like my drawing, you don't like the noisy keyboard or the squeaky chair I've heard some people complain about, then please just, any contributions help towards that. But I'm just happy to have followers as well, and I'm glad you enjoy the show. And just come watch it whenever, don't feel obligated, and I hope you enjoy it. And then until next time, if you think of any topic you want covered, just let me know, and I'm happy to change my topic. Later tonight, I'll be doing the Rust episode. I'll be programming in Rust again over at Coding Game, and that'll be done probably at 2300 hours, so in Berlin time. It's late night for me, probably not as late as night for most of you. But hopefully I'll see you tonight, otherwise next week with a few streams, and next Friday again with the algorithm and leaf streams. Thank you very much.